This is topic 5.3, the second derivative test. And mainly, the second derivative test talks about whether an extreme value is a relative min or a relative max. But the second derivative gives us concavity. So I just don't want to confuse those. The second derivative, which determines concavity, helps us determine whether an extreme value is a relative max or min. That is the second derivative test. But let's first talk about concavity. So if part of the graph is cupping upwards like this, we call that concave up. And this is where the second derivative is greater than 0. Then, if you have a part of your graph that is concave down, at any point on this graph, if you would find the second derivative, it would be negative, any point. Now, I will tell you, let me just give you a little example. You might say, well, I think this is concave up from there to there, and I think it's concave down from there to there. And your friend might think, well, I think it's concave up until about here, and then it starts to be concave down. This point where concavity changes, and we're going to learn that that's called a point of inflection, sometimes can't be determined without calculus. Let's look over here at the graph. When do we change from this concave up to this concave down? When do we change? Well, it's usually about right there. But, through calculus and things like that, we would be able to find the exact value. Here, we're just going to be estimating. So let's go ahead. Oh, the definition of point of inflection is right below that. And a point of inflection is where it's a point where concavity changes. And we look at those where the second derivative is equal to 0 or the second derivative is undefined. Okay? So we'll be looking at both of those places. So let's take a look at this graph. We first note that this is F. So we're just looking straight at concavity. So I'm just going to give some estimates. I'm thinking this might be a point of inflection. That's where we change from concave up to concave down. Let's choose this point. Now, this point there is where we change from concave down to concave up. And how about right about here? That's where we change from concave up to concave down. So let's go ahead and note that we have this interval from negative infinity going all the way to 3. And we are going to say that the second derivative has to be positive there and that we are concave up. And then from 3 to 4, we are concave down right here. So that second derivative is going to be negative for any point in there that you might find. Whoops. I'll just get rid of that. And then from 4 to 5, if you can see right here, we're concave up. And so from 4 to 5, that second derivative would be positive, and we're concave up. And finally, concave down from 5 to infinity. So looking at the graph of F, we can estimate those points of inflection. Okay? So now let's define the second derivative test. And basically, this is what the second derivative test says. Suppose that the first derivative at some x value c is equal to 0. Okay? So what did we find? We found either a max or a min, right? The second derivative is 0 there. Okay? Then, the first derivative is 0 there. Then, if the second derivative is positive, we have a relative min there. And if the second derivative is negative, we have a relative max there. Well, let me tell you, it shouldn't be that big of a deal. Here we are concave down, and so we have a max, a relative max. And here we are concave up, so we have a relative min. That's the second derivative test, right there. So we will use it, but it should be something that's very easily understood, okay? Let's use the second derivative test to find the relative extrema, okay? First things first, let's go ahead and find our derivatives. The first derivative is 4x cubed minus 4x. I can factor 4x out, x squared minus 1. We end up with 4x, x minus 1, x plus 1. And we're going to set that equal to 0 so that we can go to a sign chart. So x is equal to 0, x is equal to 1, and x is equal to negative 1. Okay? Now let's go ahead to find the second derivative, and that is 12x squared minus 4. We can factor a 4 out, x squared minus, 3x squared minus 1, and we'll just go ahead and leave it like that. We'll set that equal to 0. And we get x squared equals 1/3, or x equals plus or minus 1 over root 3. Now, what's important now is let's go ahead and make an f prime sign chart just so we can have those critical points on there, and we can see where the first derivative is equal to 0. This is where the first derivative is equal to 0, and I don't want that to look like a second derivative, so let me write first derivative, okay? So that's really important. Now we're going to go ahead and take a look at the second derivative, and that's just going to be negative 1 over root 3 and 1 over root 3. Now, if you look closely, you can use these values here. So let's go ahead and put the places where f prime of x is equal to 0 at x equal to negative 1, x equal to 0, and x equal to 1. Now we will tell what these are. If you look at x equal to negative 1, that would be here. And so we need to go ahead and put our plus and minuses on our f double chart so that we can determine what the concavity is at every one of those critical points. Okay, so let's use some test values here. We'll actually be using these same values, which is fine. So let's go ahead and put x equal to 1 here. And if x is equal to 1, here at f double is what we're putting in right here, is what f double prime of x is. And if you plug a 1 in there, that's a 4. Well, the 4 is always positive, so we're just plugging it into 3x squared minus 1. Of course, it's going to be positive. And then a great test value there is x equal to 0. And so if you plug a 0 in up there, it is negative. And then if you plug in a negative 1, you're going to get a positive. So there is our concavity chart. See if I can get that. I better make this eraser a little bit smaller. So now what do we notice? We notice that we're concave up here, concave down here, and concave up here. So that's what we have to look at our locations. So at x equal to -1, which would be right out here, we are concave up. So at x equal to -1, we're concave up. So we have a relative min. And you can put since concave up. And let's do the same thing here for x equal to 0. We have a relative max since we're concave down. And then at x equal to 1, we have a relative min since we're concave down. Okay? Let's go ahead and fill in this chart. Basically, this chart just justifies concavity. We do that with a sign chart, but some of you may like these tables. And this right here is the second derivative test. That's the actual test. We found where the first derivative was 0 and or undefined. Excuse me, where the first derivative is 0. You can see it right here. The derivative has to be 0 to use the second derivative test. And then we looked at the concavity to tell whether we had a relative min or max. This should not take much time. Negative infinity to -1 over root 3, -1 over root 3 to 1 over root 3, 1 over root 3 to infinity. That's pretty quick. Our test values were -1, 0, and 1. We saw the direct concavity be positive, negative, and positive, and we decided that we were concave up, concave down, and concave up. Let's go ahead and see if we can put this on a graph. What I did was I just found f of 0, f of 1, and f of -1. And you're going to go back into your original equation up here. And f of 0 is 0. F of 1 is -1. And f of -1 is -1. So 0, 0, 1, -1, and -1, -1. And we are concave down here and up and up. So to go ahead and just sketch that graph, just kind of come through like that. Everything's very smooth and maybe something like that. So it's kind of cool. And then these changes in concavity, if you really notice, it's probably, maybe you didn't see where I did that. Let me do it with a little purple. Somewhere around right here and right here is where our concavity changed from down to up. These are concave up. So that's about 1 over root 3 and -1 over root 3. Okay, let's go to motion. I think you will really like this particle motion. A particle is moving along the x-axis with this position function, and we want to find the velocity and acceleration and then describe the motion. So let's go ahead and find the velocity is just the derivative of the position function. So we have t squared minus 8t plus 12. Let's go ahead and factor that. And then let's go ahead and set it equal to 0. So t is equal to 2 and t is equal to 6. These are our critical points. I also want to mention, since this is motion, this is where the velocity is equal to 0. Okay, so what I like to do is go ahead and make a velocity sign chart. And at velocity, we have 2 and 6. If we use some test values and go into this velocity equation, and if I plug in a 7, I'm going to get a positive times a positive. If I plug in a 3, I'm going to get a negative times a positive. and a 1, I'm going to get a negative times a negative. So there's our velocity. So here I'm moving to the right, I'm moving to the left, particle's moving to the right, and then the particle is still for just a moment at t equal to 2 and 6, okay? So that's pretty nice. Okay, let's go to the acceleration. Is just the derivative of velocity, which is 2t minus 8. Factoring a 2 out, you get t minus 4. So the acceleration is equal to 0 at t equal to 4. So if we make a sign chart for that, for the acceleration, it goes there. Now, let's go ahead and plug in some test values. We're going to plug them in up here to via a of t. And we'll go ahead and plug in a 5 up there, and that's a 5 minus 4 is a 1, positive. And plug in a 3, we get a negative. So now we need to talk about where things are changing. Remember those graphs we looked at? So we have things going on, as you could see. I wish I could go ahead and copy this. Our velocity, I'll put it right under it. How about that? I should have written it right under it. Here's our velocity, and things are changing here at 2 and 6. So you could almost think of things changing at 2, 4, and 6. Okay? So here, maybe that's not the best, those dashed lines. Let me take those off. And let me just fill in these. Plus, minus, and plus. It's probably better like this, unless maybe I use a highlighter there. I don't know if you like that. I kind of don't. So let's just write our intervals, okay? So we have things changing on these intervals. So I'm going to go from, and we just wanted the motion. So over here we could write, and was time, of course, starts at 0. And then goes on. So from 0 to 2, from 2 to 6, and from 6 to infinity. I am moving to the, and from 0 to 2, I'm moving to the right, 2 to 6, left, 6 to infinity, right. Okay? Now, let's go ahead and over here, once we compare the acceleration, we're going to start from 0 to 2. And now we have a 2 to 4 because the acceleration changes at 4, 4 to 6, and 6 to 8. I think instead of writing infinity, maybe it should be infinity, yes. I don't know where I got 8 from. Maybe I meant infinity. Okay, so now what do you notice? From 0 to 2, my velocity is positive, but my acceleration is negative. They are opposite in sign. So the particle is slowing down here. Now, what do you notice here? From 2 to 4, the velocity is negative, and so is the acceleration. So you are speeding, the particle is speeding up from 2 to 4. And from 4 to 6, the velocity is negative, but the acceleration is positive. So slowing down. And finally, both the acceleration and the velocity are positive there. So speeding up. So that is the description of the motion of the particle. Finally, we conclude this with a really, really, really great part. The first thing I want you to know is these are F prime charts. These are not F. So what I'd like to see you do is I'd like to see you make an F double chart for these. Because the question asked about concavity, I am not going to make an F prime chart. Now, what's the relationship? We're going to look where F double prime is equal to 0 or F double prime is undefined. That's what we're going to be looking for and putting on our chart. Well, I see the derivative of F prime is F double prime, right? So where the derivative of the derivative is 0 is at -2. I also see a place here at 0, and I see a place here at 2. So, are these points of inflection? Let's look at concavity on both sides of this. From -infinity to -2, all of the slopes of the tangent line are negative. So, that means that it's concave down there. And all of the slopes are positive here. And from 0 to 2, it's also has positive slopes of tangent lines, and then they're negative from 2 to infinity. So I do want you to notice that our points of inflection are only at x equal to -2 and x equal to +2. X equal to 0 is not a point of inflection because the concavity is up to the left of 0 and also up to the right of 0. Again, you can't see that on this graph because this is the F prime chart. Then let's give them our interval of concave up and concave down. Concave up would be -2 to 0 and 0 to 2. We do want two separate intervals for those. Do not include 0 in your interval. -infinity to -2 and 2 to infinity. We're concave down. Okay, the last problem here is a really nice one. Again, this is the graph of F prime, so we're looking for the derivative of this graph. So we notice that we have the second derivative undefined here and also here. And here the second derivative is 0. And I could have put that over on all of these that the second derivative was 0. Let's get those right on our chart. I see a -1, a 1, and a 2. Okay, now this has an open interval at -4 and a closed interval at 3. So when we give our intervals and points, we need to make sure we are locked in there. Okay? Okay, let's look at the slopes of the tangent lines. They're all negative before -1, positive between 1 and 1. You see how positive that is? Negative between 1 and 2, and positive from 2 to 3. So all of those are points of inflection, are all three of those. Are x equal to -1, x equal to 1, and x equal to 2. Let's go ahead and give intervals of concavity. Concave up, -1 to 1, and 2 to 3. Whoops. And let's talk about concave down from -4 to -1 and 1 to 2. And that concludes this topic.